alpha 2 up to Pn to the power alpha n, which is also equal to Q1. But now in place of Q1 you can write P1 because we have proved this. And in place of beta 1 you can write alpha 1. This is yet to be proved, but for now we assume times Q2 to the power beta 2 etc. times Qm to the power beta m. From this we get, you just cancel P1 to the power alpha 1 from both sides, which you can do because this is a positive integer after all. We get, what do we get? B equal to A divided by P1 to the power alpha 1, which is equal to P2 to the power alpha 2 times, let me write one more, P3 to the power alpha 3 up to Pn to the power alpha n, which is also equal to Q2 to the power beta 2 times Q3 to the power beta 3 all the way up to Qm to the power beta m. Okay, now look at this. Since P1 to the power alpha 1 is after all greater than 1, it can be 1 in only one situation when alpha 1 is 0, but alpha 1 is not 0 because alpha 1 is a positive integer. So that's why the point here is that I am dividing by a number greater than 1. So the size of B is less than A. We get this. Since B is less than A, the induction hypothesis implies, okay, but there is one more thing I should write before going to this. I should write this. If B happens to be equal to 1, say after, A is equal to P1 to the power alpha 1 and which is also equal to Q1 to the power beta 1, which are equal, but there is nothing else. Both n and m turn out to be equal to 1. Then we are done. There are no more prime factors, and we have shown that actually this will be the case. Or let me just formally write it here. If B is equal to 1, then A is equal to P1 to the power alpha 1, which is equal to Q1 to the power beta 1, and we are done. Since we have shown that P1 is equal to Q1 and alpha 1 is equal to beta 1. So in this case, n is equal to m is equal to 1. Okay, so that part is we have from this situation. If b is equal to 1, pi equal to qi, since n is 1, so there is only one value of I, which is 1. P1 must be equal to q1, which we have shown here. Alpha 1 must be equal to beta 1, which we claimed to be true, which we will prove. But in this case, we will have the induction will stop here. However, if b is greater than 1, then b is greater than or equal to 2 and less than a. Less than a because we have already said that this is greater than 1. because alpha 1 is a positive integer. So p1 to the power alpha 1 is greater than 1. So on dividing a by this, we get a quantity less than a. Then this, and so by the induction hypothesis, okay, what is the induction hypothesis? The induction hypothesis says that if we have an integer less than a and greater than or equal to 2, then if that integer happens to have two apparently different factorizations, then they are essentially equal. So that means, and in that, the mathematical expression for that uniqueness is in the form of these three claims. So the first thing we will have is that now here for B we do have two representations which are after all equal. The representations give me numbers which are equal, but the representations must be shown to be equal. Now they are equal by the induction hypothesis. The first thing is that both of them should have the same number of prime divisors. Here what is the number of prime divisors? N minus 1. Here the number is n minus 1. We have number 1, n minus 1 is equal to m minus 1, which implies n is equal to m. What is the second one? The second one says this: Pi must be equal to Qi for I lying between 2 and m. Okay, after having this n equal to m, this statement makes sense. We have that many Qi's as we have Pi's. And the third one is this: the third one is just this: alpha I is equal to beta I for I varying from 2 to n. Okay, so these conclusions have been drawn from the induction hypothesis, combined with we already have proved that P1 is equal to Q1 and alpha 1 is equal to beta 1. We have number 1, n is equal to m. This follows from here itself. We already have this. Number 2, now Pi is equal to Qi for I lying between 1 and n. For I lying between 2 and n, we already have it from the induction. But additionally, we also have P1 equal to Q1. So taking that into consideration, we have this. And the number 3 likewise gives me alpha I equal to beta I for I lying between 1 and n. This is precisely we wanted to show. This shows that the representation of A as a product of primes in this way is unique. Okay, so this completes induction. Means the current induction, the second induction, and shows that the representation of A is unique, and hence it proves the theorem. Okay, so this completes the proof of the fundamental theorem of arithmetic. The one we have, the theorem 131, right? Yeah, that its name is the fundamental theorem of arithmetic because it shows that prime numbers are the building blocks for all integers. That's why the prime numbers are so important. Okay, now we come to the question of that proof part. So here I have, it's not there in the text, but I have added this as a proof exercise. It goes like this. Address the proof part in the proof of theorem 131. So this is as an exercise. So its solution. Okay, so here what we have to prove, we have, remember when this proof part, what is the proof part? It comes when we have already showed that P1 is equal to Q1, that is, we have this P1 to the power alpha 1 times P2 to the power alpha 2, etc. times Pn to the power alpha n, which is equal to, P1 is equal to Q1, so I can write here also P1 to the power beta 1 times Q2 to the power beta 2 times etc. up to Qm to the power beta m. This is before proving that n is equal to m. Okay, so that thing is entirely different. Now we have this. From this we have to somehow conclude that alpha 1 is equal to beta 1. Suppose alpha 1 is less than beta 1. We are supposing this, say. Then if alpha 1 is less than beta 1, I can divide both sides by p1 to the power alpha 1. And doing so, what shall I have? P2, let me write it there, will be more clear. Then, having divided both sides by p1 to the power alpha 1, we have p2 to the power alpha 2, p3 to the power alpha 3 up to pn to the power alpha n. So this is equal to p1 to the power beta 1 minus alpha 1 using one of the laws of exponents times q2 to the power beta 2 etc. to qm to the power beta n. Now beta 1 is greater than alpha 1, that means beta 1 minus alpha 1 is a positive integer. So since beta 1 minus alpha 1 is a positive integer, P1 divides this, the right hand side, times Q2 to the power beta 2 etc. to Qm to the power beta m. Hence, P1 divides the left hand side also, since they are equal. But then by the corollary, to lemma 132 132. I hope I am writing the correct lemma. My short-term memory seems to be suffering because of some reason. Lemma 132, yes. Corollary to lemma 132. P1 divides one of these primes, Pi, for some I lying between, now I lies between 2 and n. But this is impossible because P1 is strictly greater than Pi for all I lying between 2 and n, according to the way we have chosen these i's, these Pi's. So our supposition is wrong. Okay, I need more ink. So this supposition is wrong. Alpha 1 cannot be less than beta 1. Similarly, we can show that the inequality beta 1 less than alpha 1 also cannot be supposed. You can understand what is going to happen. If beta 1 is less than alpha 1, then you divide both sides by p1 to the power beta 1. Then on the right hand side there will be no p1 factor, on the left hand side there will be a p1 factor, and that will lead to an impossible situation. So the only conclusion is alpha 1 is equal to beta 1. That's how we get this conclusion, that alpha 1 has to be equal to beta 1. Okay, so now the proof is over. We have justified it in its entirety. This theorem is very important and it has its counterpart in unique factorization domains. We will come across that. In fact, we are going towards a study of those things in ring theory. Okay, so now this was 8, right? Okay, I have the analysis and algebra things have got jumbled on this table. Okay, give me a minute to identify the things. 5, 6, 7, 8. 9, yes. Okay, now we are going to, so these were all the number theoretic discussions of the set of integers, namely the things which arise from the Euclidean algorithm. Now we change direction a little bit and we look at the relation. There is a relation that can be formed on the set of integers. It is said to be congruence modulo n, where n is a given positive integer. This relation gives rise to something called congruence classes. In fact, in one of the recent videos on analysis, we have mentioned one example while discussing about equality in set theory. We have mentioned one example of a set of congruence classes. So we are now going to look at that. Okay, so here is the definition, and later we will see that this congruence modulo n, actually this relation can be defined in a much more general way, in a much more general context. Here we are going to define it in the set of natural numbers. In general, it can be defined in groups, and there the relation will have a much more general form, which will become this relation when we, in place of any group, we consider the additive group of integers modulo, and we will see those things. Okay, let's just first look at the definition. Okay, so let n greater than 0 be a fixed integer for any integers a and b. We write this symbol. Okay, if n divides b minus a or a minus b, it just means it ultimately leads to the same relation. We say, okay, for example, let us just first look at an example. For example, we can think of some non-trivial examples given here. 73 is congruent to 4 mod 23. Like that, 21 is congruent to minus 9 mod 10. Okay, so the n that we have here, that n has to be some positive integer, some fixed positive integer. Once you have fixed that, here in place of a and b you can have any integers. We can write like this, provided the difference of these two integers is divisible by this integer. That's the definition. Then we write like this: if a is, if we have this, then we say that a is congruent to b modulo n. When we write, it's read like this: a is congruent to b modulo n. Some authors put brackets, but Herstein chooses to not use brackets. It does not matter actually. The integer n is called the modulus of the relation. It's a binary relation. It relates two integers, and n is said to be the modulus of the relation. If A is not congruent to B modulo n, that means if this relation does not hold for some A and B, that is if n does not divide B minus A, then we write we just write it down. Okay, so this is a relation on the set of all integers. What are its properties? So to show the properties, there is a lemma. It has some parts or subdivisions. The first three subdivisions show that this relation is an equivalence relation. And the fourth and fifth, they show that how this relation behaves with addition and multiplication. So we have, do we have a fifth? No, we have only four. Okay, so let us go through the lemma, statement of the lemma. It is lemma 1, 3, 3. So the relation of this, they have to be written like parts. The relation congruence modulo n is an equivalence relation. Okay, so this is the first one. Number 2, this relation has n distinct equivalence classes. Number 3, if A is congruent to B mod n, instead of saying modulo n, we sometimes say mod n, and C is congruent to D mod n, then A plus C is congruent to B plus D mod n, and AC is congruent to BD mod n. And the fourth one is a sort of cancellation law. If AC is congruent to BC mod n and C and n are relatively prime, keep in mind that this notation means this is the GCD of C and n. We have already discussed this. Then A is congruent to B mod n. Okay, so we are now going to prove them one by one. The proof is not very difficult. The parts follow quite easily from the definition itself and elementary properties of divisibility that we have already seen. Okay, so the proof goes like this. So to prove the first subdivision, we have to show that the relation is an equivalence relation. For that, we need to show that the relation is reflexive, symmetric, and transitive. For any a, b and c. That means for any integers a, b and c, we have a is congruent to a mod n because n divides a minus a, which is nothing but 0. Any positive integer divides 0. So we have a is congruent to a mod n. What else? If a is congruent to b mod n, then, or instead of writing it in one line, let me just write it like this. We have the following. A is congruent to a mod n because n divides a minus a, which is equal to 0. So the relation is reflexive. If a is congruent to b mod n, then n divides, by the definition, n divides b minus a. But then we also have n divides a minus b. What is the difference between b minus a and a minus b? That one is the negative of the other. So if n divides 1, then n also divides its negative, which implies b is congruent to a mod n. So the relation is symmetric. Finally, if a is congruent to b mod n and b is congruent to c mod n, then n divides b minus a and n divides c minus b. So n divides b minus a plus c minus b, which is equal to c minus a. This implies n divides c minus a. So what will it imply? It implies a is congruent to c modulo n. Thus the relation is transitive. Hence, the relation is an equivalence relation. More ink. So we have proved the first part. We are now going to show that the relation has n distinct congruence classes. Equivalence classes. Now for these things to make sense, you should already know what an equivalence relation is and what an equivalence class is. I will discuss these things when we go to those parts of set theory which treat relations. So for now you just assume that I just assume that you know these things, and I move on without explaining them further. Because if I stop every now and then to explain everything from scratch, then we will not progress. We will not make any progress. So this is over. Now we come to part 2. We have to show that the relation has n distinct congruence classes, equivalence classes, sorry. Okay. For A or B are already given A, B and C, right? We are given any A, B, or C, or for the second part we are not given anything. So for, I have to consider for any A, that means any integer A, there exist Q and R such that A